Okay, we'll start the class. So we discussed the general equation of motion uh, for externally applied force. So you can have a damping component, inertial component, and the stiffness component. You can arrive to the same general equation of motion either using Newton's second law or D'Alembert's principle. So for a static problem, now this is general for dynamic, but for a static problem, we usually assume acceleration and velocity are negligibly small, even if nothing is really at rest, but the relative acceleration, relative velocity are negligibly small, so we can assume this to be zero. So for a static case, what you have is actually the stiffness times the displacement, which is a stiffness force, equals to the externally applied force. So we have more terms, let's say free vibration. When we say free vibration, it means there is no continuous force acting on the system. If you initially disturb it, let's say you have a spring mass damper system, and if you initially give it some displacement, if you initially give it some kind of displacement and then release it, then you have only an initial force. The rest of the vibration happens without continuously acting force. So your force, externally applied force term would be zero. So this is a case what we call free vibration. You'll have only an initial disturbance, then the rest of the motion is without constant force. And there is a forced vibration. Let's say you have a motor sitting on the foundation block and it's continuously applying some sinusoidal force. Let's say up and down vibration. So it's a constant force, then this is a forced vibration. So your force term is not zero. Let's see the general equation of motion for ground motion. So far it has been for externally applied load. Now for a ground motion, let's say you have, let's say, one-story building like this, simplified with a frame model. The mass is lumped at the center, and you have these columns and beam. As moved by UG, just take an instant of time where the ground moved by this much. UG is the ground displacement. If it moves like this, now it introduces different motions on the building. You will have some relative motion, you will have this total displacement. You will have this relative displacement. Now you will see some bending in the columns. This bending, the column will feel some force, especially if there is some relative motion between the ground and the one-story building. So you assume this is the part of the relative motion. This part is the ground motion. So the total motion is ut, or u dot double dot t. This is the acceleration. When we talk acceleration, we said it's double dot. So there is a total displacement, total acceleration, and there is also a relative displacement, relative acceleration. So if you see the body at the top, or the free body diagram of the one story at the top, always what you have is the inertial force, the damping force, the stiffness force should be zero, or should be equal to the externally applied force for a system to be in equilibrium. So you have the damping force resisting the motion, the stiffness force resisting the motion, and also the inertial force in this direction because the ground move here. For that case, now that's felt by the framing members is two kinds. There is one relative to the relative motion, especially the damping force and the stiffness force. There are forces stored within the frame because of the relative motion. If everything moves together with no relative motion, then the structure is not a beams and column. They are not going to feel any force. So the damping force and the damping force, they are with respect to the relative motion. However, the inertial force, it's with respect to the total displacement, or also called total acceleration. So the inertial force is the mass of that story times the ground displacement and the relative displacement, the relative acceleration and the ground acceleration. So that's the difference. Now, if you put everything together, then what you'll get is, for a ground motion, you'll arrive to the same equation, except now you have inertial force, damping force, stiffness force equals to the forcing, which is the ground force or the ground acceleration. That ground acceleration minus, just the difference is just it's a minus sign now. So whether you have externally applied force like a force on the object or a ground motion, you have the same terms all the time: inertial force, damping force, stiffness force, and the only difference is how the acceleration is acting. If it's a ground motion, it's minus times mass times the ground acceleration. So you can basically represent a building, a one-story building under ground motion, ground acceleration like this. It's the same as still resting on a rigid body with externally applied force. But that externally applied force now is negative times the mass times the acceleration of the ground. So you always will arrive to the same conclusion. Whether it is externally applied force on the object or a force coming from the ground, you'll always arrive to the same equation, except how the force is acting. So vibration types, let's just quickly summarize how many type of vibration we have. We can have periodic or regular, a sine wave, a sine function, cosine function, or non-periodic, or it can be irregular. A non-periodic can be transient, like finite time. It's a short duration of time. Or it can be steady state, like a wind load, for a long period of time. And vibration problem types, we can have free vibration, where in the general equation of motion, there is no constant force acting on it. It's zero. For free vibration, you can have with damping and without damping. So we call it damper system and damper system. For forced vibration, now there is a constant force acting on it. It's not zero. Still, for forced vibration, you can have a system with damping and without damping. So these are the four major problems we'll be discussing the rest of the chapter. You can have just a spring mass system. There is no damping and there is no constant force acting on it. So it's free vibration of a spring mass system. This is the more simplified one. Or we will have a forced vibration of a spring mass system, a little bit more complicated. Now we have a constant force, like a machine acting on the foundation, constantly applying force. So still there is no damping. When we say there is damping and there is no damping, it's how we simplified it. By nature, there is always damping. But the way we approach these problems is from the simple one to the more realistic one. So we'll first see just a spring mass system with no force. Then we'll look at with force, with no damping. Then a free vibration with stiffness and damping model, how the equations are, how the vibration characteristic is. Then finally, we will look at to the more complex, where we have everything. The soil characteristic or material characteristic represented by the stiffness and the damper. And we have also a force acting on it. Let's say in this case, a machine acting on the foundation. So this is the most complex system. But all are, we'll approach all of them with a single degree of freedom system, and we'll derive equations, see how the vibration displacement characteristic is. Then we go to the second and multi-degree of freedom system. Let's see the first one, which is the most simplest case, free vibration of a spring mass system. We call this free vibration when you have only initial disturbance. Give it initial disturbance, then let it vibrate. And we assume the soil doesn't have any damping. This is just an assumption. We're trying to approach it from a very simplistic model. So if you give it initial displacement and let it go, it will vibrate. Especially there is no damping here, we expect this to continuously vibrate. If the load causes elastic deflection of ZS, the elastic stiffness spring constant of soil is defined as the weight by the elastic displacement will give us the elastic spring constant. Or you can call it also coefficient of subgrade reaction if that stiffness is divided by area, like foundation on elastic medium. So for this vibration, what do we expect? We expect it to be periodic, continuously to continue, because there is no any damper to dissipate the energy. So this is undamped vibration. It has same amplitudes all the time because there is no damping. Time after time, we'll have the same amplitude A. That A is equivalent to the initial ZS we give it. If the foundation is disturbed from its static equilibrium position, the system will vibrate. The equation of motion of the foundation when it has been disturbed through a distance Z can be written from Newton's second law of motion as, now you'll have mass times acceleration, damping times velocity, plus stiffness times displacement equals to 0. We say 0 because it has no constantly applied force. And we also assume there is no damping, so cancel out damping. So the equation of motion is just the inertial component plus the stiffness component equals to 0. So that's the model. This is the equation of motion. It is a second degree differential equation. So if you have a weight, foundation and foundation weight W, then the mass is just W by G. G is acceleration of gravity. Z dot dot. So sometimes we are using U dot dot, sometimes we are using Z dot dot. They're the same thing. It's just what notation we are using for displacement. If we are using U for displacement, then we use U dot dot. In this case, we are using Z, so we're calling it Z dot dot, second derivative of displacement, which is acceleration. T is time, mass is mass. So if you see this equation for just a spring mass system, this is a linear homogeneous second order differential equation with constant coefficients, and the solution has the form of, this is just from mathematics or from your advanced math, or you can see also derivation in reference 6, Anil K. Chopra book. It has a derivation for this form, how we arrive to the solution form. I think it's derivation 2.1 in chapter 2, you'll see it. So the solution of this differential equation is A1 cosine omega nt plus A2 sine omega nt. A1 and A2 are just coefficients to be determined from initial condition. Depending on the initial condition, it may be displacement, it may be velocity that we give it initially to vibrate. Depending on those parameters, you'll have this Z is a displacement history. Omega n, it's the natural frequency of vibration. So where A1 and A2 are constant to be determined from initial conditions, omega n 2 pi f, 2 pi by period. We know what period is. 2 pi by period is undamped natural circular frequency. So the velocity and acceleration now, velocity is Z dot, which is first derivative of the displacement. We know that the displacement solution is this much, or it's given by this equation. So if you do the first derivative of this equation, which is d by dt of this equation, which is the same as this, you'll end up with these terms. Cosine would be negative sine, and sine would be cosine. So you'll have these terms. Now, acceleration is the second derivative of the displacement, which means the first derivative of the velocity. So you can use d by dt of this, because this is the velocity now. You can plug it in here. So you have this expression. So now we know that the solution of this differential equation is given by this z, or the displacement time history. At any time t, we can find where the displacement is. If you know the displacement history, getting the velocity and acceleration is easy. You just do first derivative and second derivative of the displacement. So you have your original differential equation for 1 degree of freedom system, pre-vibration with no damping. Substituting acceleration and displacement in the equation of motion. So now we know the expression for z dot dot, which is acceleration, and z, the displacement. You can plug that in the equation. So you'll end up with these terms. And if you solve this, finally what you get is undampened natural frequency is square root of k by m. K is the stiffness. Mass is the mass. They are input in rad per second. And the natural frequency is 1 over 2 pi square root of k by m. Once you know Wn, circular frequency is 2 pi fn, so you can easily determine this. If you know the natural frequency, then the period is just 1 over fn. So it would be 2 pi square root of m by k. Hence, substituting Wn, the circular frequency, you can simplify now the equation with these terms. So what we're doing here is we're deriving the equation of motion. We know the solution. Using the initial conditions, we determine Wn, and we plug in Wn in terms of k by m. Because we're putting the variables that we know, the constants that we know. K, we know it. Assume we determined it. In case of soil, let's say it's just, a plate load test. If you do several plate load tests and average it, you can find pretty good estimate for soil. A mass, we know our foundation block or a mortar mass or whatever. Time is time. So we're trying to find the displacement with time history. Now, A1 and A2, we said we can determine A1 and A2 from initial conditions. What we gave it initially. Did we give it velocity or did we give it initial displacement? Let's say at t equals to 0, that's when the disturbance is starting. Let's say z equals to z naught. Maybe we gave it initial displacement. We push it down or up, then we let it go. That's initial displacement. Or in some cases, we can give it initial velocity. Either both of them or one of them. So let's determine this too. Substituting for initial displacement at t equals to t0, or the initial condition, we have z is equal to z naught. At t equals to 0, you can put 0 here, sine 0 and cosine 0. Cosine 0, you'll have 1. Sine 0 would be 0. This term will cancel out. At time is equal to 0. You will have only this term. Cosine 0 is 1. So z would be A1. So the initial A1 would be whatever you have initially. That's what the initial displacement that you give. If you give it, that's A1. So you found one of the constants. Substituting for initial velocity. How about if you had initial velocity also? At time is equal to 0, if you have some velocity that you gave it. So z The first derivative of the equation of the velocity is this. And if you put t is equal to 0, then what you end up is a2 would be the initial velocity over the square root of k by m. So now we know we determined every unknown initial parameter, a1 and a2. Plug them in. If you put it back in the displacement equation, now we have all terms known. You have initial displacement, if you applied it. You have k by m, which has a vibration input parameters, the stiffness and mass, the system parameters, they are known. And if you gave it initial velocity also, you have this term, initial velocity by square root of k by m sine k by m. So this is the equation of motion for that 1 degree of freedom system without damping for free vibration. So it's like a mass sitting on a spring. Sorry for my bad drawing. So if you give it some initial displacement or initial velocity, that's how the displacement history is. Everything is known. Z naught and V naught, they are the initial velocity and initial displacement you gave it. Let's say if you gave it only initial displacement, let's say you push it down by Z naught and then you let it go. So in this case, you didn't give it initial velocity. So this term would be 0. So the displacement is only with this time history. K by M, you know it. Stiffness we know, mass we know. So with time, we can determine the displacement of this mass at any time. It's vibrating back and forth, but at any instant of time, we can say, oh, the mass is here. Or we can plot it with time. So this is where we arrived. Just be aware of how we arrived to the general equation. I don't expect you to memorize all these steps or these equations. All this is just to show you how we derived it, how we found it. We're not interested in memorizing every step, but you're expected to understand what the final output is. What's the circular frequency? What's the natural frequency for a free vibration system? And what's the equation of the displacement? You're not even expected to memorize this. But be aware what each term is, what it means to have Z naught, what it means to be V naught, and K by M, what are each terms. So if you plot this displacement expression for that vibrating mass, you will have a plot like this. This sounds familiar, looks familiar. It's a sine wave, cosine wave. It's a periodic motion. So look at the initial conditions. Depending on Z naught, if you gave it initial displacement Z naught, then you'll have some Z naught. If you didn't give it, if initial displacement is 0, then the plot will start from 0. In a displacement time plot, velocity is a slope. So that's what the slope you see, initial velocity V naught. Slope is the first derivative of the displacement, dz by dt, that's velocity. So at any point, the slope for the graph that's the velocity. So initially, at this point, that's the tangent to the curve. That's the initial velocity you have. So period, we know that. It's the time, this is a cyclic motion. So if you take one cycle anywhere, let's take this cycle. This is one complete cycle. So the period is the time it takes for one complete cycle. Or the period is 2 pi by the circular frequency. Amplitude, it's Z. Z is the amplitude right here. And the total expression is this. So the amplitude of vibration, you can simplify it further. You can derive what is the amplitude of here. The amplitude, to find the amplitude, your velocity should be 0. Or wherever the point is, where dz by dt, the first derivative is 0, which means the peak point is. If you take the first derivative of this equation and compute it where it is 0, then that's the value where the displacement, the amplitude is maximum. Or you'll arrive to this equation. Z, capital Z is the amplitude, is square root of Z naught square, the initial displacement square, plus M by K by the initial velocity square. That's the maximum you can have. It's repeating itself because we don't have a damper. It's not dying out. These amplitudes are the same everywhere. So here is what I want you to keep in your mind. For that single degree of freedom system with no damping and free vibration, we determine the circular frequency is square root of K by M. The period is 2 pi by the circular frequency. And the natural frequency is the inverse of the period. So make sure you keep this in mind. This is probably the most useful equation you'll find in vibration. You'll use it because we tend to simplify more complex vibration into a single degree of freedom system because we want to understand how it behaves, how it vibrates. And for a single degree of freedom system, we want to see what is the period. Once you know the period, the natural period of vibration of a structure, then there is a way also to determine the natural frequency of a soil, the underneath soil, the entire soil medium. So we start comparing, okay, if the vibration of the soil is this much and the vibration of the structure is this much, are they coinciding? We'll shortly see that, what happens when the two coincide. So I want you to keep this in your mind. Don't worry about the big derivations, big equations, things like that, but make sure you understand the simple outcomes. So we can have other alternative expressions. If a spring stiffness K and the weight on the spring W is known, then the static displacement, we know it. The weight by the stiffness is as a static displacement. Or K, the stiffness, we can represent it by the weight by the static displacement. So the natural frequency, we can have expression in terms of static displacement. It's the same thing, these expressions, but in terms of static displacement. Let's see a couple of examples just to show you how to calculate the equations we just derived. Let's say you have a mass which is supported by a spring. The static deflection of a spring due to the mass is 0.381 millimeter. Find the natural frequency of vibration. The natural frequency of vibration is 1 over 2 pi square root of g, which is gravity of Earth, by the static displacement. We just derived that equation. We're talking about this one. Plug that number, you'll find 25.54 hertz. These are examples on your references. This is example 2.1, reference 2. If you go to those references, you'll find all these examples. Let's see another example. For a machine foundation, a given weight of the foundation is 45 kilonewton and a spring constant of 10 raised 4 kilonewton per meter. Determine the natural frequency of vibration and determine the period of oscillation. Period and natural frequency, that once you find they are inverse of each other. So the natural frequency 1 over 2 pi square root of K by M. Put the input values, you get 7.43 hertz. Period is the inverse of the frequency. You get 0.135 second. They have big applications. These are just a simple way to show you how to calculate them, but we'll see big applications when we go through in the chapters. Does anybody have any question? Okay. Let's see the second case. Now we're going to make it a little bit more complicated. The simplest case we had was just a spring and a mass and just initial disturbance. Now let's assume it's actually we have a motor vibrating on the foundation. We have a constant force acting on the foundation. Still, the soil is assumed to be no damping. We have only spring. So we're step by step, we're getting more complicated. So the figure on the right shows a foundation that has been idealized to a simple spring mass system. Weight W is equal to the weight of the foundation itself, and that's supported by it. And we have a spring constant K to represent, let's say, the soil. So we are geotechnical, like I said before. This is the course is geared towards a geotechnical students. So most of our examples will be foundation and soil, represented in springs and dampers. But these concepts are applicable anywhere: structural engineering, mechanical engineering, aerospace engineering, anywhere. Anywhere you can model a material with a spring and damper, you'll have the same equation, the same expressions. So let's have a force, a constantly applied force, which is Q naught sine omega t plus beta, if you have some phase shift. So it's like a cyclic force acting at the top vertically. We're also simplifying the force acting on it. You can have a horizontal vibration, you can have a vertical vibration, you can have a rocking and pitching. So a machine can apply all kind of vibration, but we're simplifying it to be just a one direction for now to understand the concepts. So we have a vertically applied force. So the equation of motion is what? The equation of motion is, our general equation of motion is what? We have three of them, right? Mass times acceleration, which is the inertial component. And we have the stiffness component. Why we don't have the damping component? Can anybody shout out? Why am I missing the damping here? Anybody? Abebe, go ahead. In the general equation of motion, I have three terms: the inertial, the damping, and the stiffness components. But here I have only inertial and stiffness component and the force acting on it. Why am I missing the damping component? Abe, that's to you. Or anybody. Getu, go ahead. Oh, Getu, you are mute. I can't hear you. Anybody? Anybody? Unmute other Gunna. Let's make it more interactive class. Instead of just me talking, we'll make sure that everybody's on the same page. So that I understand you guys are following. Somebody unmute and tell me why we are missing the damping component here. ጌቱ እየተናገርክ ነው, but you are mute. How about Fakadu? Are you guys following me? Or anybody just unmute and answer the question, or try to answer. We'll correct it if somebody make a mistake. It's okay to make a mistake. Eyob, can you try?
ጥያቄውን አንዴ መደገም ከተቻለ?
ምንም ችግር የለ። Thank you, Eyob. Everybody looks like freezing. Thank you. So for this forced vibration of spring mass system, we are just discussing, I have this equation, right? This is obtained from the general equation of motion. The inertial component, the stiffness component, K times Z equals to the force. The force, we know that it came from this force. But I have only the inertial component and the stiffness component. But in the general equation of motion, I have also the damping component, which is C by Z dot. Why am I missing the damping component? It's very simple answer.
አምፕሊቱዱ ዘሴም ስለሆነ
No, no. Maybe I'm confusing you. See the model. Do I have a damping here?
ኖ ኖ
No, I don't have a damping here. That's why in the equation of motion also the damping component is missing. The damping is 0. That's my assumption. So I have only a spring and a mass. So the mass will have the inertial component. The spring will have the stiffness component. If I had a damper in the model, then my equation also will include the damping component. There are always three. In the general equation, you have stiffness, inertial component, mass times acceleration, which is caused by the mass. This will be 0 only if you are assuming a massless vibration of the mass is nearly 0. In the material assumption, if you assume both damping and stiffness, then you'll have both forces, the damping component and the stiffness component. When you analyze a static problem, it's always the stiffness component, which is K times Z equals to the force. But for a dynamic, for a general equation of motion, we have three: inertial, damping, and stiffness component. And depending on the force we have, sometimes it's 0. In the first example we saw, we call it free vibration. It requires only initial disturbance. Now, in the second case, we have actually input motion at the top, which is caused by a machine vibrating on the foundation. That's the force. You get it, yo?
የስ የስ
Okay, let's proceed. So, same equation of motion, inertial component, mass times acceleration plus stiffness component equals to the force. It's a constant force. It's a vibrating, constantly vibrating force acting on the foundation in the vertical direction. So this is also a second degree of differential equation. The solution to this differential equation has the form of this. Now it's getting more complicated. When it was free vibration for the first case, when there is no constantly applied force, it was two terms, A1 and A2. Now it will be A3. So the displacement can be expressed for this differential equation like this. You can find this solution from any advanced math book. Considering at rest initial condition, if initially it was at rest, both initial displacement and initial velocity is equal to 0, because the force causing the motion is now a machine, continuously vibrating. Let's assume initially the machine there is no initial displacement given to the mass or initial velocity to the mass. The general solution for displacement of the mass is this. Now I'm missing the complex derivation of this equation arriving to this, but you can find it in your reference books if you are interested on it. So the displacement can be given by this equation. Now you'll see more terms. Q naught Q naught is the force given by from the motor. K is the stiffness of the spring. W and Wn. Wn is the natural frequency of the mass and the spring. But W without the subscript N, that's the forcing frequency. You see it at the top right here. That's the frequency that the applied force is moving. So you have two forces, two frequencies, W and Wn. So Wn is what we know. We had a frequency, a period equation, everything. But W is given. If a motor is manufactured from a company, they will give you what W is. Its frequency when it works. So it's an input. We don't need to determine it. It's always provided. Wn also is a material property of the spring and the mass, or the soil in this case. So we can determine it. So all these are constants. Q naught is the initial force, or it's also called the amplitude. K the stiffness. So all these terms are constant. Sine omega t, omega is also constant. It's a forcing frequency. It varies. When I say constant, it's not one single value. It can vary. But we know the range of variation that the motor is working on. W by Wn sine omega nt. So all this displacement time history, you can determine it with this equation with time. If you know W, and all these constants, you can plot Z, or the displacement time history of that mass. However, Q naught by K is equal to Zs. Q naught is the maximum. When you have this expression at the top in the forcing frequency, Q naught sine omega t plus beta, Q naught is the amplitude, the force acting, the maximum force acting on the foundation. So that force divided by the stiffness is the initial, the static displacement, or it's called static deflection. If you represent M, all these terms, M is equal to 1 over 1 minus W by Wn squared. We call it also magnification factor, but I'll show you why we call it a magnification factor. You can simplify the displacement expression with this equation. The displacement given by the static deflection times M, which is a magnification factor, times the same terms right here. Sine omega t minus W by Wn sine omega nt. Now, look. Note that the magnification factor goes to infinity when W by Wn equals to 1. This is magnification factor is M. M equals to, we said, 1 over 1 minus W squared by Wn squared. If W, which is a forcing frequency, is a characteristics of the motor, we get from the manufacturer. If W is the same as Wn, the property of the spring and the mass. If the two coincide, if the two are equal, what happens? This term will be 1, right? W squared by Wn squared is 1. 1 minus 1 is 0. 1 over 0 is infinity. Or at least numerically, you will not have solution at that point. You'll be a software error. So the magnification factor, it goes to infinity if W equals to Wn. So a manufacturer for the motor, they gave you W. And if you design your stiffness and mass system, Wn, you can play with it. That's part of your design. You know how much the mass of the block, the foundation is together with the motor. And you know what the spring constant is from the platelet test. And if you determine, and if the two are matching, then this magnification factor is going to infinity. So you can see the property of the magnification factor, M, versus with a ratio of frequency. The forcing frequency, this is from the motor, divided by the natural frequency of the spring mass system. If W by Wn is about 1 ስትጠጉ, this is what happens. If you plot it, you have this chart. It's getting close, but it goes to infinity. Never touch it. It goes to infinity in both ways, either to the negative direction or to the positive direction, above 0 or below 0. What it tells you is, now, let's see this equation. This is a displacement history, a displacement expression, right? Static displacement is constant. Now, magnification factor is going to infinity when the two are equal. So what are you going to have? This is a case called resonance. That's where I'm going. Resonance is when you have excessively large amplification, excessively large displacement, and that occurs when the natural frequency of the system, our spring mass system, closely matches to the forcing frequency. In our example right now, the forcing frequency is a motor vibration, but it can be anything. It can be earthquake. If the frequency of the earthquake is equal to the frequency of the system, a spring mass system, then you will have this excessively large amplification. Now, this is just showing you the magnification goes to infinity. But look, the M goes to, at W is equal to Wn, M, we know that it goes to infinity. If you see this term, when W is equal to Wn, these two terms would be, they are going to be the same. So this could be 0. So we're going to have actually infinity times 0. One is killing it, the other one is skyrocketing it. So this is not something you can solve just by putting W by W, but you can look at it. What happens when we are really close to each other? You may not have solution when you are really at it, W by Wn, but when you are close to each other, like a limiting condition. So let's applying L'Hopital's rule, which is trying to find the solution when W is approaching Wn. That's your calculus. Exactly at W is equal to Wn, there is no solution, or it's not realistic. There is something we ignored here. In our assumption, what we said no damping for this model. That's why we say, okay, the displacement would be to the infinity. But if you have some damping, there will be a limit to how much it is moving. But you can find the solution using a limit theorem. If you do a limit theorem, if you solve this, or do the first derivative with a forcing frequency, when W is approaching Wn, you can find a simplified equation like this. The displacement would be given by half of Zs. Zs is the static displacement. Sine omega nt, Wnt plus cos omega nt. So now omega n is when W is approaching really Wn. Or that means, look what it is happening. It means if you plot that equation, this is what you find. If you displacement with time, this is what happens. Initially, you will have a smaller peak, but that peak starts growing with time. It gets larger and larger. So it's not like instantly going to infinity, but it grows with time. So at some point, the displacement is so large, the system cannot handle it. It just fails. This plot is prepared with some input. Wn, we are assuming Wn is 5 hertz and initial static displacement of 0.1 meter. But you can do it for any system. So which means excessively large displacement. So the situation where the natural frequency of a system, our foundation mass system or foundation spring system, coincides with the forcing frequency either from the motor vibration or from an earthquake, that's when you have excessively large displacement. And that phenomena, we call it resonance. Resonance is a situation where you have excessively large displacement. When we discuss first chapter, Introduction to Earthquake, we specifically mention an example on resonance. And that was the Mexico City earthquake. The Mexico City earthquake, there was excessively large amplification of the bedrock motion through the soil, and it coincides, it was about the fundamental frequency was around 2 hertz, I think. And it matches the frequency of some of the buildings. And those buildings from 5 to 15 story, they were completely destroyed because they experienced excessively large displacement. They cannot handle it. That's why. This is the explanation. This is what resonance is. Resonance is when you're forcing frequency, either from a motor vibration for a machine foundation or for an earthquake condition. If it's closely matching the natural frequency of your system is your foundation, your spring, your structure, and soil. If they are closely matching, then expect excessively large displacement. And that's a resonance phenomena. Well, the good news is if we know this happens, we can work around it, which means we need to design our structures, our system to be away. We need to avoid the frequencies from being close to each other. So that's our design philosophy. So this is just showing you the same thing, same resonance phenomena, how the displacement grows. Since the velocity is equal to 0 at the point where the displacement at the maximum, for max displacement, you have your displacement equation we just derived. The velocity can take the first derivative, and the velocity would be 0 at each peak, right? Which means it's the opposite vibrations. Whenever it's the other extreme, velocity is 0, then returns back. So finally, the maximum displacement, you can determine it as half of n. N is because the cycle is continuing. First peak, second peak, third peak, fourth peak, goes on. N pi Zs. Zs is initial displacement, the static displacement. So as time goes on, this is just the first 5 seconds. An earthquake stays, let's say, 30 seconds, 40 seconds. So the more shaking you have in your system, if frequencies are coinciding, then the displacement is growing. There will be very large displacement on the structure. At some point, the structure cannot handle it. It just breaks, cracks, fails. That everybody understood what resonance is? Yo, is that clear?
Yes.
Okay. Thank you.
Mm.
So let's see what maximum force on foundation subgrade is for the same model. For W equals to Wn, when the forcing frequency coincides with the natural frequency of the spring mass system, resonance occurs. And dynamic force on the foundation excessively increases on the foundation as Z increases. So this is a situation in our design we try to avoid. That's why we predict earthquakes. We try to predict earthquakes. We know how much frequency, how much the system frequencies around the structure. We know what the soil character is. We do borehole tests, geopropagation tests, anything, trying to understand what the soil natural frequency is. And we design our structure. So we try to make sure that the soil frequency at least is different from the structure frequency. We don't want them to coincide. And if earthquake comes and it coincides together, then that's the total collapse. So we try to avoid it. But if the two are not equal, that's what most of our design is. natural frequency different from the forcing frequency, the max displacement can occur when the velocity is 0. So you can have a displacement expression with this equation. This is what we saw before. And velocity, the first derivative, can have this equation. Now, at max displacement, we know that velocity is 0. It's like a pendulum. When the pendulum swings, at the peak displacement value, velocity is 0. So this term will be 0. Solving for t and back substituting, you'll find z max. Max displacement is given by the q naught, the initial force given by the spring constant, over 1 minus w by wn. So you'll see this w by wn constant. It's everywhere. And it's clear that when w by wn is 1, then you know that 1 minus 1 is 0, then the displacement is going crazy. So we try to avoid that. If you know the initial displacement or the displacement, the force is just the stiffness times the displacement. So even if it's a continuous dynamic motion, bit by bit, any instant of time, you can assume it like a static force, continuous static force acting on it. The force dynamic acting would be the k times the dynamic displacement at that specific time. So it's given by this. Q naught, the max, you have a motor vibrating on the foundation. The motor has a max force amplitude of this much. We know the forcing frequency of the motor. We know the natural frequency of the spring mass system. If you know the two, then you know how much force is going to the foundation from the motor. The maximum dynamic force is Q naught over 1 minus W by WN. This is the dynamic component. But you have also the static component. Static component, because the motor is sitting on the foundation, then it's W, right? So when the motor is vibrating up, you have less force acting on the foundation because the dynamic component will be subtracted. But when the vibration is downward, you have the static component plus the dynamic component acting together. So it will be additive. So the dynamic component we just found, you can do plus or minus on it, and you'll have the minimum and the maximum forces acting on the foundation. Let's say a simple example. A machine foundation can be idealized as a mass spring system. This foundation can be subject to a force that can be given Q is equal to 35.6 sine omega t. It's continuously vibrating force. And amplitude, you have 35.6. That's a peak value. Given F is equal to 13.3, this is a forcing frequency. Weight of the foundation and machine, 178 kilonewton. The spring constant, let's assume we already did our soil test and everything. So the spring constant for the soil is 70,000 kilonewton per meter. Determine the maximum and the minimum force transmitted to the subgrade. So you have a foundation block, you have a motor sitting on the foundation and applying sinusoidal force. And what we are trying to determine is you have the soil medium underneath. How much force is acting on the soil going to the subgrade? So the natural angular frequency of the spring mass system for the soil, Wn is K by M. We know that. And mass is the mass of the foundation plus the mass of the machine. K is the spring constant for the soil. So we know that it's 62.11 rad per second. This is the natural frequency of our system. Our system is the mass and the spring, or the mass and the soil. But from the manufacturer, from the motor manufacturer, we are also given the frequency of the motor vibration. As they said, it's 13.33 hertz. So the forcing frequency is 2 pi f, which is 83.75 rad per second. Now watch. We don't want the two to get close to each other. We don't want them to be equal to each other at all. If you get a motor from a manufacturer and you know its circular frequency, then you need to work with the stiffness and the mass in your design so that they stay away from each other. So the dynamic force acting on the subgrade is, we know that it's the expression we just derived in the previous page, is Q naught over 1 minus W by Wn. Put those numbers. You have your dynamic component. So the maximum force on the subgrade, static and dynamic, is from the static, which is just a weight. Static weight is 178 plus the dynamic component. That's the maximum force acting when the vibration is downward, putting pressure on the soil. So you have 280 kilonewton. When the motor is vibrating upward, that's the least force you can have on the foundation. That would be 178 minus 1 or 2.18, 75.82 kilonewton. With these forces now, you can determine, okay, how much settlement I'm going to have. Is the bearing capacity of the soil good enough to carry all this? If it's not, then you work with your design. Maybe you make your foundation block bigger. So when you make it bigger here, the mass increases. And when the mass increases, then what happens? The natural frequency decreases. When Wn decrease, what happens? When Wn decrease, this would be constant. So this number will be larger. So it decreases the dynamic force. So you can play either with the stiffness. Stiffness means you may be, replacing the soil. If you have a softer soil, you may want to make it more stronger soil. Instead of clay, you may prefer sand. So K increases. So you should play with K and M so that you can reduce your dynamic force. So you have another course, machine foundation, but these concepts are exactly on machine foundation, even though they are applicable for earthquake too. That's how the whole concept is. You play with your stiffness and mass system and play with the system so that you're varying your natural frequency of your design from the input or from the motor frequency. Stay away, the two shouldn't be close to each other. When they're close to each other, this gets really crazy. You can put different values for W and W and see how it goes. Right here you can see it, W by Wn. If I'm designing my foundation system to be close to around 83.75 rad per second, then W by Wn is going to be close to each other. When this is close to each other, this term, the denominator, is going near to zero. When it is near to zero, then the dynamic force is excessively large. So the idea is to minimize the dynamic component. So that's part of the design. Does anybody have any question? Is it clear what I'm saying? Yob, is it clear?
Yeah, for me it's clear.
Anybody has any question? This is very important concept. Resonance, the concept of resonance. Try to avoid the two natural frequencies not to be close to each other. They cannot be same. It can be, some motors, they work with, either at a larger frequency or at a lower frequency, but they cannot work continuously around the natural frequency of the system, because you'll have excessively large force and at some point it fails. It takes some time to develop. Like the failure mode, it's not like instant, but you may see some forces increasing, displacement increasing, cracks being observed on the foundation. Then at some point when it may take hours before it completely collapse. So this is probably a new concept for most of you, what resonance is. But resonance is in simple terms, with these simple examples, with 1 degree of freedom, that's what it means. But it happens the same way with complex system. When you model your structure, thousands of degree of freedom system, you'll have different modes of vibration. When earthquake comes, then if it's close enough, then you'll have excessively large forces acting on the structure. That's why you see cracks. That's why you see collapse. Some buildings collapse, some don't. I showed you in the Mexican City earthquake, a tall structure, it survived. It's barely damaged. Maybe window crack, minor crack in the walls and floors. But a shorter height, like 5-story, 8-story, 10-story buildings, they completely overturned. They couldn't handle it. Why? Because the natural frequency of the earthquake and the soil, it was closely matching those natural frequencies of those buildings between 5 and 10, 15 stories. Taller buildings, they were not close enough, so they survived it. So we'll come back again and again and again in this. When we discuss resonance, we'll go more detail. This is just the first phase, trying to make you understand the concept. The other concept is okay. So the next one is free vibration of the spring mass damper system. So we understood now the concept is from the first two. In the first two, we had just the stiffness and mass and free vibration. In the second case, we saw stiffness, mass, and continuously acting motor vibration on it. Now we're getting to the third case, a little bit more complex. We're introducing damping, because in reality, it doesn't vibrate continuously. At some point, the energy die. We need to incorporate that concept in the model. And the mechanism where the energy die, the energy gradually decrease, we model it as a damper. So this third case is where the stiffness, and we're introducing damper and mass system. And depending on the damper, the times 3, displacement times 3, it may be one of these 3 cases. It can die out quickly, very large damping, like 1 and 2 case. We call it over damping and critical damping, or under damping. This is the most natural case in our systems. Foundation soil, this is more, it die out slowly and disappears. But you have system which completely die out in one shot also, like a car jack, hydraulic system, piston. So energy at some points in reality, it decreases. It decreases gradually. It die out at some point. So that concept is damping. So this is the third case. So dampers, for example, in this case, we can see viscous dampers. Viscous damper is those hydraulic systems. If you open it up, a damper, you can see, it works with a fluid. In our soil example, it's actually, between particles, there is a friction loss. When there is friction, there is a heat generating between the friction surface. There may be sound also. There are different ways where the energy dissipates. But when we say viscous damper, which means it's a material damping, whether you use a fluid like in a piston, or in soil, whether it's lost because of a friction, because of rearrangement of particles, or permanent deformation of the particles, one or the other, there is a way the energy is dissipating. If it's a material related, then we call it viscous damper. There is another form of damper also. We briefly discussed it in the previous class, the radiation damping, but we will come to it. I think in chapter 5, 6, or 7, we'll touch it. what it means and how energy dissipates because of radiating, or when you have like a geometrical spreading. So the viscous dampers, this is like a material damping. This material damping, you can have examples like in high seismic areas, like in the western part of US, or somewhere in Japan, in Taiwan, in the Asian countries. There is a high seismic areas. It's common to see buildings where these dampers installed within buildings. You have a column, beams, in between there is a piston system with a fluid in it. It's like usually like an oily fluid. So they are trying to dump out the energy. So it's part of the framing structure. So when a shaking comes, when the building vibrates, this works as a damper. Or the simple damper, the hydraulic jack for car. You hold it, you do your job, and finally when you release it, it slowly dump out the energy. So the car doesn't, come and impact. Slowly, it's like this one is like a critical damping case. It's a damper. Or you have dampers for bridges installed. Or you can have a damper with springs, in playground areas or supporting machine in workshop, anywhere. This one is a damper, like with piston system. And there are springs. So you can have multiple type of dampers. But for our geotechnical section, when we say damping, it's within the soil particles. You can have like a permanent deformation in the soil, particles sliding one over the other, friction loss, all that system or settlement, that will introduce the damping or the energy dissipation. So now, for free vibration of 1 degree of freedom, such as foundation on a spring, the differential equation of motion can be given by. Now, that differential equation of motion is a general equation of motion. We have three terms, right? For anything vibrating, or even in a static condition, you can write this equation. The mass times acceleration, which is the inertial component, plus the damping time velocity, damping constant time velocity, which is a damping component, and the static component. Static component is the stiffness times the displacement equals to 0. So now I have all three terms because I have all three now. I was missing the damping component. Now in my module, I'm getting more complicated. So I'm including the damping component. Stiffness and mass, I have it, and I still have it. But in this case, what I am missing, I'm assuming free vibration. No forcing frequency on the foundation. This is the third case. In the most complex case, we'll add it, and you'll see it, what it looks like. But for this case, let's assume a system under free vibration, but stiffness and damping. So the solution of this differential equation, it has the form of this Z A e to raise to RT. You can see any advanced math books for this, or your reference book, they have it. Now, if you solve it, you'll end up for R, you will have this quadratic equation solution form. Now we're going to have multiple cases. This is a solution of a quadratic equation for R. And by the way, you can arrive this equation, but just by doing the derivative. If Z is this much, then do Z dot dot is second derivative. And then Z dot dot you can represent, put it here. That's the mass times acceleration. Then find the first derivative and put it with the damping. If you do all that, you have this quadratic equation, and its solution is C by 2m plus or minus square root of C squared by 4m squared minus K by m. These are all known parameters. C is the damping constant. Mass is constant. So we know them. If we know them, then we can find a solution for it. So there are three general conditions that may be developed from this equation. One, C by 2m greater than square root of k by m. Now look at it in this form. If C by 2m, this C squared by 4m squared, it means C by 2m the whole square, right? If C by 2m is greater than k by m under square root, which means we're trying to see the k's when the term under the square root, whether it is 0, less than 0, or greater than 0. Those are the three cases. When C by 2m is greater than k by m, this number is positive. So we have a real solution. So both roots are real. So it would be minus C by 2m plus or minus that real number. They are real and negative. This is referred to as an overdamped case. If C by 2m is square root of k by m, if these two terms, this guy right here equals to this, so it would be 0 under the square root. In that case, it would be critical damping case. If C by 2m, if the term under the square root is less than 0, if this C squared by 4m squared minus k by m is less than 0, then we're going to have a negative number under the square root. And square root of negative number, we have a notation, I, square root of minus 1. Now we're getting into complex numbers. This is referred to as the case of underdamped case. This is a more realistic situation. But it will be more clear when we go through it. So let's define a term called damping ratio. Damping ratio, this is very common. When we talk about damping in your finite element modeling, we usually talk about in terms of damping ratio. It's the damping of the material divided by the critical damping. The critical damping CC is 2 square root of km. The critical damping C square root of km is the part which makes the square root term is equal to 0. It's this. The case where we have critical damping is when the square root term is 0. So the critical damping is always 2 square root of km. K and m, stiffness and mass are material properties. So you know the critical damping case. But if the actual material damping divided by the critical damping, that's called damping ratio. So we usually talk about damping ratio. So it's going to be unitless because we are dividing it by the critical damping. So at this condition, when we have a damping ratio, then you can have, the expression, the previous expression in terms of D, in terms of damping ratio D. And now, if you see it, R, it was mass and K and M. Now we explained it in terms of D, which is damping ratio. Let's see case 1. Case 1 is overdamped condition. That's when D is greater than 1. We know that the square root inside the square root, it's greater than 0. So it's a real solution coming out. So that's the overdamped case. That's the pattern you have, like the one shown in 1. The solution of the differential equation is this. So for R, when you have this, you can back substitute. Now you have R, back substitute R in here, and find a solution in Z. If you do all that substitution, you'll have this complex Z, or time history equation for Z. We're representing it in terms of time. So you can determine the displacement of that mass vibrating with damping because everything is constant. Wn is constant, d is constant, except t. V naught and z naught are the initial conditions. So you can arrive to this equation. Or in general, if you plot it, this is the pattern you'd find. Number one, overdamped case. If you're interested more in the derivation of this equation, please feel free to look at your references. I put the link here. See derivation in reference to section 2.5. You can look at it just for your own mental satisfaction, but we're not interested in the derivation steps for this class. We need the final output. We want to see how structures are behaving, but the derivation steps, if that interests you, please look at this section. And I'm not expecting you also in this class to memorize equations as long as this. That's not the point. If there is a test or a homework, these equations are always available. For your design, they are available. What you are expected to understand is how to apply them, what it means to have all these terms, that engineering mindset. We're not like expecting memorizing or anything. No, you don't have to. But make sure you understand each term, make sure what it means, make sure what it means over damped case, under damped case, or critical damping case. Let's see case 2, critically damped condition. That's the red chart here, displacement with time plot. That's it. That's a time when the D, the damping ratio, equals to 1. The damping of the material is the same as the critical damping case when it is 1. Then the displacement equation would be like this. It's just in terms of initial displacement, initial velocity, natural circular frequency, initial displacement, time. So time is the only variable here. You can plot this in a MATLAB or Excel or anything. Case 3, under damped condition. Under damped is when the material damping is less than the critical damping case, or when D is less than 1. That's when we said we'll have more complex solutions too. But we'll be focusing on the real part, but the complex part also comes together. That's a more realistic vibration scenario for geotechnical engineering. You can see how when an earthquake comes, it just gradually vibrate, and it die out. Or if you swing a pendulum, gradually the peak decreases, the amplitude decreases, and at some point it becomes negligible. The other two cases are like something like a piston in hydraulic systems. A critically damped case. It's a high damping value in their case. But in most natural cases, like soil has critical damping ratio about, I think, a damping ratio of about 15, depending on what type of soil you have, 10 to 20. Can be higher for loose soil, can be lower around 10 for stronger like gravel soils. Concrete has damping ratio of around 5 and 7. But hydraulic systems can be even more than 1. Very high, or 80%. So case 3, under damped condition, this is the most realistic case for our case, for civil engineering. This is where we'll be focusing, where the damping ratio is less than 1. So the displacement time history, you can arrive to this equation. Gets more complex. Still, if you are more interested, feel free to look at the sections in your reference. But in plots, you can see it also, how the vibration dies out. If you plot this in MATLAB, Excel, MATCAD, or anything, you will see it like this with time. Okay, we can stop the class here for today. We'll continue next week.